All right, I wanted to do a video over the review. It might turn into videos. I'm not really sure. I'm not sure where this is going to go. I'm going to start with limits. First one is limits by a graph. Just remember what the minus and plus mean at the top. That means from the left and from the right. So if I'm approaching -2 from the left, that means I want to go towards -2 from the left of -2. So where does it look like my y value would be if I continued from the left of -2, which would be 3. If we're approaching -2 from the right of -2, that means we're going to go to the right of -2 and follow back on the graph, and that appears as though we're going to positive infinity. When you get rid of the distinction left and right, remember those have to match up for the general limit to exist. So that's why that doesn't exist, is because these two answers are different. Okay, so if we did, the next one is 6. 6 from the left. 6 from the left would be 2. 6 from the right is 5. If I asked the general limit as x approaches 6, that also would not exist because those are not the same. For example, as x approaches -8, from both the left and the right, the limits would be -6. So the limit as x approaches -8 is -6, even though the actual y value at -8 is -3. So this doesn't have to be the same. It's just that as I'm approaching, I need to be going towards the same place. Okay, so that's how you handle limits from a graph. Limits algebraically, you have some options. The first thing you should always try to do is plug in the number. So on like C, I just plug in 1. If you plug in 1, you get the square root of 9, which is 3. As long as you get a determinate form, which is not 0 over 0 or infinity over infinity, direct substitution works. Okay, so if you can plug in 1 and you get a value for that, that's what you do. If you do get 0 over 0 or infinity over infinity, you have some options. You can use algebra, which is what I did. I essentially factored the bottom into x plus 6 and x minus 6, and then I canceled the x minus 6's, and then I resubstituted. Another option that you would have on that same problem is if you get infinity over infinity, you can use L'Hopital's rule. And L'Hopital's rule is that I would just take the derivative of the top and the bottom separately. So the derivative of x minus 6 is just 1. And the derivative of x squared minus 36 is 2x. And then I could plug in 6 and I would get the same answer. So anytime that you can use L'Hopital's rule, it does usually make things easier. B, I got infinity over infinity. I used L'Hopital's rule. I did the derivative of the top, which is 4x, and the derivative of the bottom, which is 9x squared. Plug in infinity again, and again I got infinity over infinity. So I used L'Hopital's rule again, where I took the derivative of the top and the derivative of the bottom, and then plugged in infinity. And then on that third time, I got 4 over infinity, which means I'm dividing 4 by numbers that are getting larger and larger and larger, which means that's going to tend towards 0. Okay, so that's basically limits. What you need to know about limits is limits from a graph, how to do those, and then limits algebraically. I'm going to skip over a few things here. I'm going to talk about the theorems all together. So I have that one of your questions will involve a major theorem. There's basically 3 of them. 2 of them are in this unit. The squeeze theorem and the intermediate value theorem. There is also the mean value theorem. I would consider that to be a pretty major theorem. I'm going to talk about those a little bit later on, either in this video or in another video. So I'm just going to skip those for right now. I'm going to jump down to derivatives. You don't have to do any definition of a derivative, so that's where you do this limit as h approaches 0, and you do a bunch of algebra. I'm not going to make you do that. Basically, the limits that you're going to have, the derivatives that you're going to have will just be some basic maybe products, quotients, maybe some that are just like a polynomial that you got to take the derivative of. But don't forget to look for those types of things. So 2a here, it's a product rule. I have e to the x times sine x. So we do the first times derivative of the second plus second times derivative of the first. Okay, so just a very basic product rule there. B is a very basic quotient rule. I've got a division problem, so I do the bottom times derivative of the top minus the top times derivative of the bottom all over the bottom squared. So really that's the square root of x squared, which just turns into x. You also have the chain rule. So if I were doing C, the first thing I would do is I would rewrite this as the cosine of 3x to the 1/3 power. And then remember, when you have a chain, you're doing the outside first and keeping everything inside the same, and then you just work your way inside. So the first thing I'm going to do is the rule for a power, which is multiply that down, subtract 1. So that's going to give me these two things, but notice that cosine 3x stayed the same. Then I go to the next insidemost function, which would be the cosine part of that. The derivative of that is negative sine, but the inside part stays the same. And then the last part would be the derivative of 3x, which is just 3. So that's a double chain rule. But if you can do some pretty basic product rule, quotient rule, chain rule, again, even some that maybe just are polynomials, you might have to rewrite them in terms of like rational exponents or negative exponents, things like that. But if you can do some very basic derivatives, you should be pretty good to go on the final. Okay, so I'm going to skip down to, let's see, applications of derivatives. The main thing here is curve sketching. I will say on the final, I'm going to organize this a little bit more for you in terms of knowing when the first derivative, or when to use the first derivative, what that tells you, when to use the second derivative, what that tells you, things like that. But remember, when we do curve sketching, you know, you have, and again, you're going to have a graphing calculator, which is going to help a ton here. But these first things, domain, if it's a polynomial, all real numbers, x and y intercepts, again, you have a graphing calculator, so you'll be able to use those. And the asymptotes, if the domain is all real numbers, you're not going to have asymptotes here. So all of that is from the original function. Then we take the derivative of this. The first derivative is going to start in here, and that's where we look at intervals of increase and decrease and local maxes and mins. So the first derivative, I did it over here. Factor that down, set that equal to 0, and remember, those are our critical numbers. We put those critical numbers on the number line. We pick a number from each one of these intervals, plugging those into the derivative. Do not go back to the original for that. So I picked probably like -1 here, probably 1/2, and then probably 2 were the three numbers that I picked, and I plugged them in to my derivative, and all I care about is if it's positive or negative. So if I plugged in -1, this would be positive, this would be negative. If I multiplied those together, I get a negative, which means my graph is decreasing from negative infinity to 0. This first one. Between 0 and 1, if I plugged in 1/2, I would get positive times a negative, which again would be negative, and again decreasing, so that's this part. And if I plugged in, say, 2, I get a positive times a positive, which would be positive, which means my graph is increasing, and that's this part here. And then local maxes and mins, anytime that you switch from increasing to decreasing, or vice versa, you're going to have a max or a min. We go from decreasing to increasing at 1, which means if you think about the graph, if it goes from decreasing to increasing, there's a minimum there at 1. To get the y value for that, that is when you go back to the original function. So if I went back to the original function and plugged in 1, I would get that. Once again, I will remind you, you have a graphing calculator. You should be able to see that point at 1, 1. And then intervals of concavity and inflection points, you do the exact same process with the second derivative. So I take the second derivative, factor it, set those equal to 0, put those on a number line. This time, positive numbers mean concave up, negative numbers mean concave down. If you switch concavity from up to down or down to up, we call those inflection points. So since I switched from concave up to concave down at 0, there is an inflection point at 0. And again, I switched from concave down to concave up at 2/3, so there is an inflection point at 2/3. Again, to get the y values there, you go back to the original to plug those in. Okay, so that is curve sketching. Again, I think it's going to be laid out pretty nicely for you. If you have a graphing calculator, I think you should be able to get a lot of that information, but you are going to need to show the first derivative and second derivative and finding those critical numbers. So again, mean value theorem. I'll go ahead and talk about those theorems real quick, and then I will probably create a second video where I get into integrals and things like that. I know that I still need to talk about related rates and optimization. I'll get into that in just a minute, but I'm going to go ahead and talk about the theorems. This review sheet that I gave you that's got all these formulas and everything, you're not going to have this, but you'll have a very condensed, modified version of this. I would look through it. It is helpful information, but all the theorems are on the second page of this. They're all listed right here. And what I would look for is, what I'm going to be testing on is your ability to just know what the theorem says. What is it telling us? So I would look at these theorems. I wouldn't necessarily worry about applying these theorems. What I would worry about is identifying these theorems and knowing which one is the one that I'm referencing. So the intermediate value theorem just deals with essentially continuity. So we have a sum function that is continuous over some interval. So we're saying it's continuous over the interval from a to b. The idea is if the y values of a at a and b are different, then the intermediate value theorem says there is guaranteed to be a y value in between those two y values that maps to an x value between these two x values. Okay, that is all the intermediate value theorem says. Notice that in the intermediate value theorem there is no limits, there's no derivatives. It's just about continuity and how if I go from a y value to another y value, I've got to cross through essentially every y value in between those two in order to make that happen. Okay, that's the intermediate value theorem. The squeeze theorem, notice, deals with limits. Okay, so if you are looking at limits, you probably are looking at the squeeze theorem. The squeeze theorem says that we have three functions where I have two functions that are always on the outside of some third function. So I've got a function in the middle. Okay, and you can see that clearly here through this picture. G is always between h and f. What this says is if the limit as x approaches some number for both f and h is the same thing. So my top function approaches that value from both the left and the right. The bottom function approaches that same value from the left and the right. Again, that value being L. Then the conclusion is the limit as x approaches that number of the middle function also has to be L. It's squeezed by the top function and the bottom function, making it have to go to that same exact location. That is what the squeeze theorem says. Again, the key there, you're dealing with limits. Rolle's theorem is just an application of mean value. So the mean value theorem is the major one. And what I want you to notice about the mean value theorem is that it deals with derivatives. The mean value theorem says this. Again, we have some interval a to b. The y values are not the same, so it kind of starts out the same way as the intermediate value theorem. But if you see this, right, this is the slope of the line between the endpoints of a and b, right? So if I have the point at a and the point at b, and I find the slope of that line, that's how I find slope. Y minus y over x minus x, that's all we're doing there. The mean value theorem says that there's some x value between a and b. So here's a, here's b. There's some x value in between where f prime of c, so f prime of that number, that is the slope of the tangent line at that value. Okay, so derivatives are the slope of the tangent lines at that specific point. So the slope of the tangent line at that x value is equal to the slope of the line containing the endpoints, which means if two slopes are equal, we have parallel lines. So that is what the mean value theorem is saying. It's saying that the slope of the line containing the endpoints there's going to be guaranteed, if the function is continuous and differentiable, there's going to be guaranteed an x value between a and b in my interval where the slope of the tangent line at C is the same as the slope of the line between the endpoints. We've got parallel lines. Okay. So in the question involving a main theorem, those are the three main theorems. Again, what I would focus on is can you recognize those? Do you know which theorem is being used to show something? And again, I know that when we did tests over these, I made you write out a bunch of stuff and apply the theorems. It's not what I'm looking for here. What I'm looking for here is can you identify them? Okay. We go back to the review. I'm going to stop the video here. So we've covered limits, we've covered derivatives, we have covered curve sketching, we've covered the theorems. On the next video, I'm going to jump into related rates and optimization. And then from there, we'll take it to integrals and applications of integrals, and we should be done. So I would anticipate the second video to be about the same length as this one, where I'll talk about all those topics. But again, what my focus is here is that we're just kind of hitting the basics. If you watch this video or both of these videos, I do think that it would help immensely on your test and kind of just knowing what to look for and what to do.